So today I'm going to talk about analysis of simple electrical and simple mechanical systems. So there's a few fundamental things we need to know about electrical circuits. One of the components we're going to have is going to be resistance, represented by a resistor in a circuit. And as we know, we're going to have the relationship that the voltage across the resistor is going to be equal to the current flowing through it times its resistance, so V equals IR, which is obviously Ohm's law. And of course we have to use appropriate units, so the current's going to be in amps and the voltage is going to be in volts. And the resistance will be in ohms. Another aspect of simple electrical circuits is going to be inductance, which also resists the change in the flow of current, basically. And the relationship between voltage and current is that the voltage across an inductor is the inductance multiplied by the differential of current with time, so di dt, so V equals L di dt. We can also integrate this expression on both sides and then divide through by L, and in which case we'd get the current is given by 1 divided by L multiplied by the integral of the voltage with respect to time. Again, current is in amps, voltage is in volts, and inductance is in henries. Another valuable and extremely useful component we have in electrical circuits is the capacitor. And for a capacitor, the current flowing through the capacitor is given by the relationship I equals C dV dt. So the current basically depends on the rate of change of voltage across the capacitor. Again, we can integrate both sides of this and we end up with a simple relation that the voltage across the capacitor equals to 1 divided by C multiplied by the integral of current with time. Again, current is in amps, voltage is in volts, and capacitance is in farads. We can also have the relation in terms of charge Q equals the capacitance times the voltage. In fact, this comes directly from the integral form, since the integral of current over time is actually the charge that we've actually got in the system. Let's think about a simple first order circuit. And I say first order because basically what it means is the system is going to be represented by a first order differential equation. So here we just got a voltage source, and it's driving current through a resistor and a capacitor. So we've got a resistor here and a capacitor here. So obviously we've got to add up the voltages in this kind of circuit. So we can do that quite easily. We can just say that the source voltage here has got to equal the voltage across the resistor here plus the voltage across the capacitor here. So Vs equals Vr plus Vc. And then we can write what we know about the voltages and the current relations across all the components. So we use, first of all, Ohm's law, because we know the voltage across the resistance is going to be the current flowing through it times its resistance. So Vr equals IR. And we know that the current going through the capacitor is going to be the rate of change of charge with time, which is equal to C dV C dt. So it's going to be the capacitance multiplied by the rate of change of the voltage across the capacitor. So we can then write, we can basically substitute these things into the first equation. We substitute them into the first equation, and then we end up with a simple relationship. The voltage that we apply equals RC dVc dt. In this case, we're just leaving the voltage here as the capacitor voltage as it is. In this case, then we can write a simple relation. We just basically have to rearrange this differential equation. We want to get the differential in this case onto the left-hand side. So we just divide through by RC, and then we end up with dV dc equals 1 divided by RC multiplied by Vs take away Vc. And we can see that is a first order linear differential equation. We can also think about the current in another simple circuit, an inductance in series with a resistance. So here we have, again, we have a voltage that's going to drive this circuit. We have a resistance R, an inductance L, and then we're going to switch it on at time equals 0. Again, we can add up the voltages across the resistor and the inductor, and we then substitute again in for current. So VR equals IR. In this case, we've got the voltage across the inductor, V equals L di dt. So we can substitute these both into the first equation, and we end up by having Vs equals IR plus L di dt. The next thing we can do is rearrange it in terms of di dt, because this is the highest differential term. We put that on the left. What we're going to then do is we're going to divide through by L again, and we end up with the relation R divided by L multiplied by Vs over R minus I. And again, that's also a first order differential equation. We can make things a little bit more complicated by having an inductor, a capacitor and a resistor in series. And we're going to end up with a second order differential equation in this case. So this is actually going to be a second order system. So this is what our circuit's going to look like. Again, what we can do is we can work out what the voltages are across the components in terms of their component parameters multiplied by the current, or in this case, inductance multiplied by the rate of change of the current. And in this case, the voltage across the capacitor is 1 divided by C multiplied by the integral of the current with time. So we can add up all of those contributions. We get the voltage across the resistor here, we get the voltage across the inductor here, and the voltage across the capacitor here, and they've all got to equal the applied voltage. We can do a simple analysis of a parallel RLC circuit. In this case, the voltages are all going to be the same across the components because they're all in parallel. So we can then just go through and add up what the contributions are to the current in terms of what goes through each component. So obviously, the current going through the resistor is going to be V divided by R. The current going through the inductor is going to be 1 over L integral of V dt. And the current going through the capacitor is going to be C dv dt. So we can add up all of those contributions, giving us our final equation. The current going into the system equals V over R for the resistance path, plus 1 over L integral of Vt dt for the inductance path, plus C dv dt for the capacitance path. So just quickly to summarise then, for a resistive element, we have a simple voltage current relation, V equals IR, that's just Ohm's law. For a capacitor, current equals C multiplied by the rate of change of the voltage across it. And for an inductor, V equals L di dt. And this is just writing it in simple term in the comments. V equals IR, as we know, is Ohm's law. We can also have the version of a capacitor in terms of charge. So charge equals, Q equals CV, Queen equals Victoria Cross, they used to say for that. And L, of course, is in Henry's. We can actually do something quite similar now for mechanical components. We've got some simple mechanical things that we can do, which are very much like the components we have in electrical circuits. One thing that we use a lot is a spring, right? And a spring is something which is going to resist being stretched. You can get rotary springs as well. We'll come to that in a second. But basically, we pull this spring at resting length. There is no force needed, and we define the extension from how far we are from the resting length. If we then pull this thing, what we're going to get is a displacement from the resting length. As long as we don't pull it too far, it'll be a linear displacement. And for this linear range, we can say that the force we apply is equal to the spring constant times the extension we're going to get. So F equals kx. And we're going to use force always in newtons, and K is going to be newtons per metre. We can get torsional springs, so quite often you'll build systems which rotate. A typical torsional spring would be one in wooden clothes clips that you hold things up, or the pegs that you hold things up with on a washing line. In this case, again, it's got a resting angle, and if we push it with a torque, this time we rotate it with the torque rather than pushing it with the force, sorry, we're going to get an angular displacement away from its resting position. In this case, we're going to have the relation that the torque equals torsional constant multiplied by the angle. And typically the torque is going to be Newton meters, and we're going to have spring constant in terms of Newton meters per radian. Another aspect of mechanical systems which are used a lot are things like dampers and dashpots. Basically, this is something to resist movement proportional to velocity. One example of a damper would be like in the shock absorbers you have in a car, which basically try to damp out movement. So it'd be like moving underwater. It pushes you proportional to how fast you're moving, or at least within certain ranges of speed that you're moving around. So there's a shock absorber there for you. In this case, when we actually consider a linear displacement dashpot, the relationship is going to be that the force is equal to this viscosity constant multiplied by the rate of change of displacement. So in other words, it's going to be force equals velocity damping constant multiplied the speed at which you're actually moving. Actually, I should say velocity. So force in newtons, viscosity in Newton seconds per metre. Another aspect of mechanical systems we can't get away from quite often, even though we'd like to reduce it, is actually inertial mass. Now, inertial mass, of course, resists force according to one of Newton's laws. So force is proportional to acceleration. So force, in fact, we say is mass times acceleration, and we can write that as the second differential of displacement. So F equals m d squared x dt squared in this case. So force in newtons, mass in kilograms, acceleration in meters per second squared. If we're rotating, though, we need to care about moment of inertia as opposed to inertial mass. And this, pretty much in the same way as mass opposes linear motion or linear acceleration, this is opposing angular acceleration. So an example of a flywheel, for example, on a little tiny steam engine, you want this to have a large moment of inertia so it basically keeps going, and it resists actually slowing down. So they put flywheels on this kind of thing because this driving mechanism only provides, if you like, a torque for part of the cycle, and you rely on the inertia of the flywheel to pull it round so it gets back to the next time it actually has to work in that way. So in this case, we're concerned with torques then and moment of inertia, and the relationship is going to be torque equals moment of inertia times the second derivative of angle, which is angular acceleration. Okay, so torque in Newton meters, moment of inertia in kilogram meters squared. We can put that all together in simple mechanical systems. I'm just going to show you a mass spring damper here, which is one particular example. When you look at this kind of system, first of all, you have to think about, how do the forces from the different components actually add up to the external force. In this particular case, we're in the situation that if we try to pull this mass, right, with an external force, it's going to move the system, right? The mass is going to move, and we're defining movement of the mass as being our displacement x. But we can also see if we try to pull down m, the spring constant is also going to try to resist it, right? And the damping from the dashpot is also going to try to resist it. So in this particular case, if we pull down, the inertial mass is going to try to stop the system moving, and we know force equals ma. The spring is going to move away from what condition it was, and it's going to extend further. And the dashpot, you're going to be moving this viscous thing, which is also going to resist movement. So let's write down the equations then. The force basically to stop, well, to resist from the spring is going to be force equals kx. So k is the spring constant and x is its displacement. The force from the damper is going to be its viscosity c in this case, multiplied by dx dt, so it cares about velocity. And the mass is going to resist, force equals ma, and we're just writing force equals m d squared x dt squared. And the reason we're doing that is because we care about x, and we don't want to write this as a, and we don't want to write this as v. Everything's got to be in terms of x, and then this is just basically x as it is, the first differential and the second differential of x. So if I then say, let's write the equation, what's the external force equal to? We know all of these three components contribute, and they add up. So we can just add them up. So the force equals m d squared x dt squared plus c dx dt plus kx.